here's like an overview of, let's say, statistics or theory of statistics, a little bit more than theory. So we have models, or let's say categories of problems. And then we have methods and then analysis of methods. So this course is mostly like focused on analysis of methods. Okay. So like we're gonna see the models and methods in the passing, but the main idea is trying to figure out how to analyze, like theoretically analyze. Let's say mathematical guarantees, what type of mathematical guarantees we can give. So for example, how to compare estimators. So let's say, I'm going to assume that you know some of the stuff, like you know what point estimation or hypothesis testing is, but we're going to get to that. But how to frame the problems in a mathematical framework so that we can analyze them, okay, properly. And so so the main idea is like what I'm going to start is like decision theory, so that there's a framework that we can use to basically analyze everything that we do, and that framework sort of is like a unifying theme. Towards the end of the course, we're going to talk about asymptotics. What happens when the sample size goes to infinity and the theory simplifies, sort of. And this is the classical setting. So we're going to start with like, what is a notion of optimality, or like what kind of notion of optimality we can define. So how to compare estimators, what is a good estimator, what is the best estimator, something like that. And the properties of estimators follow: unbiasedness, admissibility, things like this. Okay. So that's the general sort of big picture. Any questions? So I'm going to start with this idea of decision theory. It becomes a little more clear once we dig into the details. So like statistical decision theory has it's like a bunch of ingredients, and let's say the first main component is like a probability model, which is a collection or a family of probability distributions indexed by theta. Indexed by some parameter. So there is like a distribution, a probability distribution, but in contrast to probability, or like if you want to say probability measure, in contrast to like usual setting of probability theory, the statisticians don't work with a single probability measure, or like with a single probability distribution. There is a collection. And we don't know, for example, so these are supposed to model the data generation process. So you assume that the data is drawn from one of these probability distributions. We don't know which one, and we want to decide which one. So you start with a family of probability distributions. They're parameterized. So this family, in our case, often parameterized by some parameter theta in some space omega. So this is fairly general at this point. Okay, so if I give you theta, you can pick out that particular probability distribution. So these are, each one of them is a probability distribution or probability measure for some data point x that you draw from this. So the idea is that I'm going to draw, later we'll see, I'm going to draw x from p theta. So this script x is like the sample space. Omega is the parameter space. So we have a sample space from which the data is drawn. We have a parameter space which specifies which probability distribution we use to draw the sample from. Then there's the action space, the set of available actions or decisions. That's where the decision theory part comes in. And then there's a loss function, which tells you if I pick an action and a parameter, how much loss I will incur. So it becomes a little more clear why we talk about loss and things like this. But an example of a loss is like if I have an action which is binary, 0, 1, and a theta which is binary, let's say if my action matches the theta, then I don't pay anything. If my action doesn't match, then I pay a price of 1. 0, 1 loss. For let's say continuous variables or vectors in RD, you can, for example, use a quadratic loss. So let's say omega and a are the same. And so you have this possible loss. Okay? And then the action space and parameter space need not be the same. So you can take an action in some space, omega, like parameters from some space, and then you define a loss between them. Okay, so what does this loss mean? Or like what is the nature of the problem? So the statistical inference problem, you can view it as a game in this framework. So nature, or whoever generates the data, takes a true parameter theta from this parameter space. So that specifies a probability distribution and draws x from this probability distribution. So x is a random element of this script x. The statistician sort of observes x, okay, observes x and makes a decision, delta x. So this is going to belong to that action space. So this mapping from x to an action, so you can think of it as a function. Okay, delta is really a function. And this is called the decision rule, or in statistics, it's called an estimator. We can call it something else, but this is the main thing that we are after. So that's our main job. And then statistician incurs the loss, which is L theta and delta x, okay? So that's where the loss comes in. So if you imagine that the action space is the same as the parameter space, and the action actually, you can think of it as like your guess of the actual parameter. So you can think of this A as like a guess of theta, then this makes sense. So these type of losses make sense. So if my guess is exactly equal to the theta, the true theta that I'm paying no price, but if I'm far away from it, it pay a price depending on the size of the error. So that's my loss. So that's where the ideal loss comes from. But the framework is more general. So delta could be any, like the A could be any action space. For us, it's going to be just the same as the parameter space, and delta x we interpret as, so often A is just omega, and we interpret delta x as an estimate of theta given x. Okay, so that would be my estimate. Sometimes write it as theta hat. Okay, so theta hat equals delta x if you want. But this is not necessary for the general problem. So one issue is that, okay, so I have this loss, but this loss is random. And so it depends on the particular x that I chose, even if everything else is deterministic. So then people decided, okay, we're going to minimize the expectation of this loss. So that would be deterministic, and that's called the risk. And so that's the whole game of decision theory. So you set up the problem, and then you have this risk, you have a decision rule, and you have a risk. And then you try to minimize this risk. Okay, that's the goal of decision theory. So far, so good. So any strange kind of notations here that people are, should be at least one strange notation. Everything sort of checks out. Yes.
So could you explain the E with the sub?
Great. Yeah, so that's the strange notation. So this part. Okay, sorry. So this. So anyone knows why, or like what do we mean by this, or why do we put a theta there? This turns out to be quite critical.
With respect to theta, so we can estimate it.
With respect to theta is good, and we are trying to estimate it, but maybe a little bit more formal. So what exactly? Yes.
Data expectation over the true distribution of data?
Yes. Okay. So we take the expected. No. Okay, not the distribution of theta. The true distribution of x. Okay. So the only thing random here is x. This distribution is p theta, and the distribution depends on theta. Okay. So this expectation theta is really the expectation operator associated with this p theta. Okay. So if I change the theta, the distribution changes. And if you think of the expectation, it's an integral with respect to the distribution, so the expectation also changes. So this just ensures, like informally emphasizes that this expectation depends on the true parameter data. Technically, it's just the expectation operator associated with this, because this depends on data. This is also going to depend. Okay. This is the part which is different from probability theory, right? So you have a single probability distribution, not a single probability, but it's single underlying measure, probability measure, a single underlying expectation. Here it depends, like, because we can change the probability distribution. So does that answer the question? It becomes a little more clear once we go a little bit further. But that's what I think we keep in mind. I sometimes might drop this, but it's implicit in our assumption, or like in the setup. So this thing really depends on theta twice, or in two ways. Once because of the dependence of the loss, and the other one because of the underlying dependence of the distribution. Okay, so this makes that explicit. It also depends on the decision. So it's really a function of both theta and the decision, the true parameter and the decisional that you chose. So there's no randomness. Okay, sounds good. Good.
Can you explain the loss functions a bit, like what you mean by the was not equal to?
Okay, so this one, the 0, 1, so this notation is like an indicator notation. So we're talking about this, right? Okay. So this notation is my way of writing an indicator. So this is saying this is equal to 1 if theta is not equal to a, 0 otherwise.
It is a parameter, and a is also a parameter.
Generally, like in this case, yes, because I'm assuming omega and a are like the parameters stay the same. You can look at it as a parameter. So this is your guess of theta. And so really you can think of it as I'm applying L theta and theta hat if you want. Okay, so this is saying if theta matches theta hat, then I don't pay a price. If it doesn't, then I pay a price. And this theta hat happens to be like this delta x. Okay. Any other questions? Yes. It's not an exact, like, precise statement. It's not different. It's just the viewpoint that you start from a family of probability distributions, as opposed to, in probability theory, you can also have multiple probability distributions. Usually there is an underlying probability distributions, and then random variables are defined on top of it, and then each one inherits a probability distribution, which is called like distribution of that random variable. But there is some underlying fixed probability distribution, like probability measure that controls everything. Here we often don't have that, right? You will see there's usually a measure if you want to be measure theoretic. I don't know how many people here are like interested in measure theoretic detail. There's going to be a measure underlying everything at some point, and then we'll have density to figure that. But the thing is, we start off with like a collection of probability distributions at the start for a random variable x. Okay. You can connect it to the probability theory if you want. You can say, okay, there is a probability measure underlying everything, and then there is a map that maps it to this x. That map depends on theta, so I get multiple distributions. The distinction is not quite, it's not a significant, like, deep distinction. I'm just pointing out that the statisticians like worry about multiple distributions at a time. Okay, there are alternative competing explanations. That's the thing. Okay. There's no fixed. In the end, like this is gonna assume that there is one true distribution, but you don't know it, so you're gonna keep all the possibilities at hand, and then you choose from. Okay, sounds good. Okay, good. Any other questions? Yes.
I'm just a little bit confused about the loss function.
Okay.
So data is unanswered, it's like the true parameter.
Yes.
And the little a is an actual increment in data.
Not by the data. It's just so at this point it's just a deterministic variable. I give you data and an action. You tell me how much I
Also,
pay.
we don't say that. It is given.
So if you think of it as a game, like say one side knows the data. So let's say there is like a game, there's nature, there's statistician. Statistician does not know data. And nature knows data. And there's someone like the third person decides who gets to pay who. Okay. So this guy picks data. But nature picks data. Like player one picks data, draws this. This is player two. Use the action that the X. And then the statistician like compares its loss. You can pick up the nature as giving like the negative of this. Okay. So this is like just a way of scoring how did we do. Okay. So if you pick theta, if player one picks theta, player two picks delta X, this is how much they're gonna lose. If it happens that they match, let's say this X is very informative about the underlying data, then this might be very close to data, so you pay very small price. If this is very uninformative, so let's say nature picks data, and then just randomly takes X. It has nothing to do with the data, so there's no dependence on data. Then you're gonna pay a good price because there's no way for you to figure out what data is from it. Right, the simple case, like, okay, so maybe I give you an example. So the simplest case is like, for example, the model would be X's. There's more simple than X. We will have an example shortly. Let's say X is normal 0, not 0. Between theta and variance 1, for example. Okay, if I give you, so nature picks theta, then draw X from this, and then based on X, you want to guess what theta is. Your guess might be, so what is your guess here? So if I give you X, and you just know that it's from this value, you don't know the actual theta. What's your guess of theta? Okay. There's no sample mean, it's just like give you one population. It's just X, yeah. So your guess would be, my potential guess would be X. Okay, and if my like loss is quadratic loss, in this case it's a univariate, would be theta minus a squared. Right, I'm gonna plug this like L theta delta X would be theta minus X squared, and then the risk would be expectation theta and then theta minus X squared. Right, so what would that be? This is like delta X. Right? The expectation of who's talking? Okay.
I think it will be 1.
Why?
Because the variance of the normal distribution is 1.
Right, so this is basically expectation. So this is a normal random variable minus its mean squared. So this is really the variance of it. I'm gonna put a variance theta, but happens to be that the variance doesn't depend on theta in this case, so it's gonna be 1. Because that's the price that we pay. Okay. So if it was like the model was actually something like this. So I'm going to give you the model. So this is shared between you and like all the players. Player 1, player 2, they know the model. You don't know the actual theta, but you know this value from the start. This is one A, the one decision theory problem. This is another one. It's a theta at 0.01. Right? So I'm specifying the family. So if you want to be formal, P theta is this. And so P is just a family of P thetas where theta is in R. And then X is drawn from P theta, which is just equivalent to X drawn from normal theta and 0.01. So what is your estimator in this case? What is a good action or estimator? What is a good action? What is a good estimate of theta? Still X, so it's still like this is the same. And then you go through this argument, and the risk would be in this case, it would be 0.01. It would be the variance, so the risk is smaller because of the like, it's more informative if you pay less, right? So you see the idea of thought. So this is like you're going to be more accurate even with a single observation. You're going to be more accurate than this measures it. Okay. This is a harder problem. This is an easier problem. Okay. Sort of. Yes.
I'm sorry, I'm just like getting the like perspective. So we have like subscription that like use your like how directly to like
Which part?
the last one. I think like
This one?
yeah, yes, subscription of the last one. I mean, I understand that like a variance of that, the last one that.
Oh,
yeah,
yeah.
yeah. I understand like why you think that's the variance specs, but like how to directly draw it from the expected.
So let's see which line is so this last line, right? So is this part okay?
Yeah,
Okay, and then this is okay, right?
yeah.
And what I'm saying is this is the variance of X. Why? Because so this notation is saying, okay, I'm drawing X from P theta. So the P theta here is there. What it's saying is that we are drawing X from this distribution. Under this distribution, X has mean theta. Okay, so this is really the mean of, you can say, okay, this is a theta of X if you want. If it's hard to think of theta, just draw theta. This is the mean of X. Right, so X minus its mean squared, and then another expectation, so this will be the no problem. Another way of seeing this, under this model, I can write this as X is really theta plus Z. This is another Z in normal 0, 1. Right, and then we can find this is equivalent. So this model and this model are equivalent. Right, it's in theta plus Z, where Z is 778. If you go back to review the properties of normal distribution, this model is the same as that. Then this would be just the expectation under theta of Z, but that doesn't have theta. There's just B1. But this is Z squared. This notation takes a while to get used to. At the start, it is hard just like drop theta. Okay, so there is some fixed data underlying. But as we go through, it's helpful. Once you get used to it, it's helpful to keep track. Yes.
We were making a guess out of the X that are expected muscles bigger.
That's a great question. So we get to this. Okay. So what kind of guess you want to make? So that's actually the good, the use of decision theory is trying to figure out what would happen if I do a different thing, right? So I can try to come up with a different estimate, and then you can measure its risk. What, like, is there any other candidate here? You want to try other act?
Best guess.
It's not so like it's not so clear that it's the best. Like, we're gonna get to it. Is this really the best? Yeah. I'll give you an example. Maybe this is an example that's gonna come up, but let's do it here. So delta x is cx, where c is less than 1. I can try to shrink it a little bit. Okay, you'll see what happens. So, what is the risk in this case? So this is a definite decision. Let's say c could be like 1/2. Okay, I could try to do that. So r theta and delta would be expectation c x. So how do we calculate this? C squared. Is that really true? Why?
I think the risk might depend on the distribution of theta in this case.
There's no distribution for theta. So the good thing to remember is like at this point theta is just a parameter. Okay. Theta is a fixed parameter. There's no distribution, but it will depend on theta. I guess. So how do we calculate this? What is the obvious thing to do? Expand. Okay. Theta squared plus c squared x squared plus minus 2cx. Okay, there's a theta. Sorry? Is this better? Okay. So what's next? Right, so expectation is linear, passes through. So you get expectation of, so it's good to go like slowly so that everyone is on board. So expectation is a linear operator. It's like linearity of expectation. So I can do this. And by linearity, I can do a little bit more here. So these are constant, they come out, right? So this would be really minus 2c theta expectation of x. This is a constant, also c squared expectation of x squared. And this is constant, comes out. So you get theta squared plus c squared. So what is the expectation of x squared? Yeah, okay, variance. I want to put theta, but really doesn't depend on theta in this case. Plus expectation of theta squared, right? Oh, sorry. Yeah. Expectation of x squared here. Minus 2c theta. What is the expectation of x? Theta, because we're under this model. So times theta. So this would be theta squared. This we know is 1. Right, so you end up getting theta squared plus, if you haven't made a mistake, c squared theta squared minus 2c theta squared. Right. Tell me if I'm making a mistake. Is that true? Yeah, okay. Yeah, this doesn't look very nice. Here's a c squared, there is okay, so let's do this. So let's collect theta squared here. I get 1 plus c squared minus 2c. So is this correct? Right? Okay, so I get 1 minus c squared, theta squared plus c squared. Is that true? Did we do it correctly? Okay. Okay, let's do another way where you can check. So the idea here is like a better approach is to like add and subtract the mean of cx. Okay, so what is the mean of cx? C theta. Okay, I add and subtract. So when you add, like when you square, the first comes out like 1 minus c theta squared plus c squared. The second one would be expectation of theta minus x squared. And then there's a cross term. There's a cross term which is going to be like twice like twice this times that, and then the expectation, but the expectation passes through if this expectation is 0. So the cross sign goes away. So that's the easy way of doing it. So I get, it seems to be correct. Okay, so theta squared 1 minus c squared plus c squared, right? So assuming this is correct, you can see things are a little bit complicated, right? So this one depends on theta. So if I gonna plot, so this is the key issue that we're gonna get to. We were gonna get to, but you already see it. So this risk depends on theta. So if I want to compare these two estimators, I have to really plot this entire risk function. So one of them, the first obvious one, just has a constant risk at 1. This guy, c is less than 1. Like let's say c is 1/2, for example. Or let's say c squared is 1/2. For simplicity. So it would be here at 0. Right? Theta 0 is like that. And when it's gonna hit the 1, there's gonna be 1/2. Okay, maybe not. Okay, let's do this. Yeah, okay, c squared 1/2. It's gonna hit this at some point. And it's gonna go up. Right. The way it's gonna be like that. So one has this risk. The other has the other one. Okay. So you can see immediately the problem. So which one is the better estimate? Yeah, okay. So because the theta side is inconclusive. Okay. So we can't say necessarily that this is even better. It's somehow better in a sense that this is going to be constant and it's going to be very bad for growth. But if theta is really small, then the range. But really theta is close to 0, this one is going to be better. So this is something that we have to grapple with. Yes.
How many we have like infinite number of estimators to worry about, because we can arbitrarily use some other estimators.
Yes. So that's where we want to go. So is there a way that we can like reduce the number? So is there an optimal estimator? So do you have to worry about like infinitely many estimators, or there is an optimal one? Yeah. That's where we try to go. Okay. But we have to somehow resolve this. Even in this very simple example, you can see the main issue. Okay, risk is a function of theta, and two functions are not necessarily going to be comparable. Sounds good. This makes sense. So oftentimes in our course, you can calculate the risk like this, right? Using properties of expectations and stuff, but there are formulas for this. You can write it forward. I'll maybe talk about that a little bit. But if there's no questions, is this clear? So this procedure we did is called shrinkage. So you shrink a little bit, and this has some very dramatic effect in higher dimensions. We'll talk about that. So this is the formal way of like writing these things. You may not need it, but if you want to, this you can think of it as a random variable. So it's a function of x, so another random variable. I'm going to take the expectation with respect to the distribution of x. So there's a resulting probability theory that you can just integrate this function against the distribution. That would be the expectation. And this notation is just a measure theoretic notation. Don't worry too much about it if you're not comfortable with it. But if you know measure theory, this is the way of writing it. Oftentimes we assume that these distributions have a density with respect to some underlying measure. Again, this is measure theoretic. And if you're not comfortable with, just imagine this measure mu is just Ex. So that's the Lebesgue measure. So for a continuous random variable, we have an density in Ex. But hopefully you have seen some measure theory. So if there is an underlying measure mu, which is fixed, doesn't depend on theta, and then all these p thetas. So p theta is the distribution, has density level p theta. This is now a function with respect to mu. So this is the setting we often work with. So there is an underlying measure, mu, which in the continuous case would be Lebesgue measure, if you know what it is. And then the densities with respect to Lebesgue measures are usual densities that you see like Gaussian, uniform. And in the discrete case, mu is usually the counting measure, and then this density would be really the probability mass function. So that's how like measure theory unifies everything. But the thing is that the people would be confused with this notation. P theta with blackboard phase. Like these P theta versus the low P theta. I hope the distinction is clear. Okay. If it's not clear, we can talk about it. But one is a probability distribution, probability measure, the other is a density. Okay. The main difference is like basically you integrate. So P theta is the probability measure is a set function. So P theta of A can be written as the integral of this density against this measure over A. So the difference is this is a set function assigning numbers to sets. How to assign it? This is like a function on X. They're related by this formula. So you integrate. Yes.
Is capital P, is that a CDF?
No, it's not a CDF. It's the distribution. It's a measure. So it's like probability measure. CDF is cumulative distribution function, right? And so the CDF in this case would be P theta, let's say T, or let's, okay, X mapping. If you like this function that maps X to the P theta of -1 and X. So this is a function, this is the CDF. Takes X, outputs the probability of observing, like it just outputs the probability for any X, gives you the probability that I'm in this interval.
So what exactly is the difference between capital P and lowercase p?
So P theta is a probability measure. So you need to know what probability measure is to make the distinction. And then P theta, little P theta is the density, density function, density of P theta. Another measure. So mu is a measure, which is not necessarily probability measure. So it could be like the mu of the entire space of 1. So this requires a little bit of measure theory. If it's too confusing, we can discuss it in the office hours, or you can ignore the measure theory, but it's just that this is like an abstract distribution. Okay. This is really a function that we think yes. It could be Lebesgue measure, but we don't necessarily need to. So there are some conditions like sigma finite measure, but for the most part, yes, Lebesgue measure or the counting measure. Yes. But at the level of measure theory, it can just be very abstract. What we need is that this measure does not depend on data. If you do it, that's it. So this is called the dominated family. The family is dominated. So this is a family of probability measures dominated by mu, which means that all of these have density respect to a fixed mu. That mu is an independent thing. Okay, then I can sort of ignore this distinction. I can just work with these densities. Okay, so we're working with dominated families. Classical statisticians worried about cases where the family is undominated. There's no single measure that they can use. any countable family, you don't need it's take the measure to be the sum of all. But there's a technical issue. We don't want to go into the details here. Okay, like too technical for this course. Good. I hope this is clear. So if you just do dx, then you treat this as like density of a normal. So in our case, for example, in this case, here, so p theta is the normal distribution, really. I'm going to say it like this, which is like the distribution that tells you how to assign probabilities to any set, any reasonable set on the real line under the Gaussian measure. We can take mu to be the Lebesgue measure on the real line on R. And then p theta of x would be this nice formula that you know, 1 root 2 p e to the negative x squared. Minus theta squared over 2. Right. So density is theta and integral is like this density dx. Okay. Sounds good? Sort of. Okay. Question? I'm going to move away from this because this is more of a technical notational issue. So this is actually the simplest example, probably. That's also a simplest example, depends. But this one has sampling involved as well. Okay. Suppose I observe a sequence of Bernoulli trials. I have a coin. I flip it n times, and each time I record the outcome as either 0 or 1, heads or tails. So I get a sequence of binary variables, and I can put them in a vector so that x would be this vector of binary variables. Okay. I'm going to assume implicitly that these are, like the coin flips are independent, so these are IID draws from a Bernoulli distribution. Okay. What is a Bernoulli distribution? The distribution, yeah. It's simpler than the binomial. It's just binomial with one trial. It's just the distribution of a general like 0, 1 variable. So a binary variable has a very simple distribution. You just have to specify what is the probability that it's 0, what's the probability it's 1. Okay. Bernoulli theta means this random variable takes value 1, probably theta, and variable like probability 0, probably 1 minus theta. Okay. Bernoulli is just a general distribution of a binary variable. Theta is just probability of being 1. Okay, so one possible model is one possible. This setting is like how you want to set it up is up to you. That's what I'm going to set it up. So I'm going to assume that the observation is a sequence of binary observations 0, 1, 0, 1, 1, 1, 0. Each one is a draw from Bernoulli. These are IID for some theta that I don't know. Okay, I'm going to assume that there is the same theta. It's the same coin. So if the theta changes, it's going to be a different problem. Okay, the same coin flipped. So that's one way of modeling. Okay, contains the observations, contains the family of probability distributions. The family of probability distributions can be really the distribution of this. So the distribution of this is formally the distribution on the binary cube. So each realization is being an element of this set. So this set of 0, 1 to the n is called binary cube usually, or like Hamming cube. It's just a set of binary, like 0, 1 basically, sequences of length. And because I'm assuming these are IID, I'm specifying the distribution. So Bernoulli theta specifies the marginal distributions, but because they're independent, defines a whole joint distribution. Okay, which in the language of measure theory probably is this product measure. It's a product. So if you have a bunch of marginals, like single, like you have a bunch of random variables, they have, and like they have marginal distributions, there is a joint distribution that we can put on them by assuming they're independent. It induces a joint distribution, which is called the product. That's what we do. If we didn't assume independence, then this wouldn't be enough to say that individually I'd have to specify the joint distribution. But you're implicitly imposing that. Okay, this simplifies a lot because these are simple objects. Okay, sounds good. Again, this is like a technical notation. I'm just doing it a little bit for people that are interested in formalization. We're gonna dispense with this. At some point, these are all going to be in the background. We don't specifically specify that this level will be. So that's with dp theta. Theta varies in 0 to 1. So I have a family of probability distribution in this cube, the n dimensional binary cube. And then omega is 0, 1. So how do we specify this p theta? We can do it via the PMF. And again, because it's a product distribution for the product measure, we just have to specify one of the marginals that we can get to all the time. So the single marginal is like this. So p so p theta of xi is equal to x. Let's say the I coordinate is x. The probability is equal to x is theta, and x is 1. 1 minus theta is x is equal to 0. And this is a compact way of writing that. If you haven't seen, this is a very nice way of compactly writing. Just because x takes either 0 or 1 value. So if x is 0, then this is going to be 1. Theta to the 0 will be 1, so I did 1 minus theta. Otherwise it is. So this is equivalent to that. So that's what we do. So this PMF is really that little p theta if you want. This is oh, actually, this is not p theta. Okay. So this defines the PMF, and the joint PMF is going to be the product of these because of the independence. Okay, so this p theta of x1 up to xn is going to be the product of these guys for the xi. So these are marginal PDFs or PMFs. And then I take a product because they're independent, so that's the joint. That's how we have specified like this one to give for this. So this is like probability measure, this is the PMF. That's easy to work with this guy. Okay, I don't have to worry about the measure anymore. Okay, so that's the specification of the probabilities family. And you can see the dependent data. If I change data this thing, action is exactly the omega, and then loss is the quadratic loss. Okay, so that's our specification of the model for this problem. Sounds good. So this gives you everything you want to be able to calculate. So technically, these integrals will now be summations because this is something there. So I'm going to be summing over all possible x's. So this would be sum over x, which is x1 up to xn of this guy, and then p theta of x1 up to xn. I have to sum over all possible sequences. But we really don't do that. There are simpler ways of dealing with these problems. Okay, so that's the thing, right? Any questions? So let's do the comparison of estimators that we did in this case. So what is a natural estimator of theta, let's say? Sampling. So who said that? Okay. Sorry?
The percentage of
Can you say it louder?
the percentage of having observing.
Yes, the percentage of having, like, how many ones you observed by the total number of observations, which is equivalent to the sample. Right? So xi is a binary. So when you sum them, you take the number of ones and then divide by n. So both of you guys have the same estimator, so I'm going to call this delta 1. Okay, I have it here. So delta 1 sample mean. Okay, so this counts how many ones we have divided by the total number, fraction of that. The risk of this turns out to be theta times 1 minus theta over n. We can do the calculation, or because I did one above, maybe I come back to it very quickly, okay? But it's the same idea. So you don't need to do the summation, you can use the property as a expectations. I'm going to propose some other estimators. The constant estimator 1/2. The risk of this is easy because the expectation, this is the loss. I think expectation is going to be the same. So this is really the risk. This is strange looking estimator. But it's going to be that. You can do the calculation. And then I throw all the data out except 1. And the risk of this would be theta times 1 minus theta. This is also simple, sort of. But these are some of the calculations that you can do. So let's very quickly do maybe the first one, the sample mean. How do I calculate the risk? Let's write it as x bar. Anyone tell me, like, maybe walk me through very fast, because I think we spent time doing the other one. We can do the trick that I mentioned, right? So let's do the trick. This is going to be expectation theta. We are using the quadratic loss, so delta x squared, which is going to be x minus the sample mean, x bar n, sorry, theta minus that. Okay, the trick with the quadratic loss is to add and subtract the mean of the estimator. So I'm gonna, that would simplify a lot of things. Expectation of x bar plus expectation of x bar minus x bar n in the square. Okay. Yes. So then I'm going to square, I get expectation of theta minus expectation of theta x bar n squared plus expectation of x bar n minus x bar n squared plus the cross term, plus the expectation of the cross term. But I let you, sorry, did I make a mistake again? The cross term. And the cross term goes away. 0, yes, you can verify that for yourself, okay. So what is this term? This is really the variance, definition of the variance of x bar n. What is this? Why is it 0? Okay, expectation of x bar n is theta. So you're a statistician, you probably know this by heart. So how do we derive this? Want to prove this? This is really theta. Sum of xi's over n. So 1 over n comes out. We move past the summation because of the linearity of expectation. Linearity of expectation. So this is expectation of individual ones, they're Bernoulli, right? So the expectation by definition is like 1 times the probability that it's 1, which is theta, plus 0 times the probability that it's 0, which is 1 minus theta, this happens to be just theta. So you get 1 over n, these are all theta, you get n times theta, you get theta. Okay, so this is theta, so this is also going to be 0. So the risk is really variance of x bar n. So what is variance of x bar n? Sorry. What is the variance of the sample mean if you have IID? So the sample mean of an IID sequence, basically. Yeah, it's going to be 1 over n times the variance of one of them. So basically variance of like x1 divided by n. I'm going to maybe prove that as well for you. But what is the variance of x1? What is the variance of a single Bernoulli? It's theta times 1 minus theta. How do we do that? It's just the variance of this guy is just expectation of x squared minus expectation of x squared. But x squared is just x because it's Bernoulli. This is going to be theta. It's going to be theta squared. So you get theta times 1 minus theta. So this is divided by that, and that's the Klein risk bound. Okay. So really, this is, you can think of it as this is the variance of the risk in this case, the quadratic risk of sample mean is just the variance of the sample mean, which is the variance of a single observation divided by n, and this is the variance of a single observation. So this is a fast way of doing it. Why this is true, I'm just gonna do it like a very quick note, variance 1 over n summation xi. So 1 over n comes out as squared. That's what happens in variance. So I get variance of summation xi. And this is going to be the summation of the variances. Not always, but because we have independence, right? This is true. And so variance of, they're IID, so this is going to be n times the variance of one of them. So you get n variance of x1 divided by n squared. So you get variance of x1 squared. And then I'm missing thetas, but you can just put thetas here everywhere. You can really see the variance depends on theta. Okay, the distribution, and it's not like the normal case. A Bernoulli, both the mean and the variance depend on theta. So there's really value in putting theta there to remind us. Sounds good? Okay, and then the other calculations you can do this we can do by brute force or by clever methods, but the main thing about the quadratic loss is that things simplify if you do this trick. And this will, I'm gonna like record it later in a lemma. This trick leads to this, and this has a name. Anyone knows what the name of this is? There's some sort of decomposition here. Bias variance decomposition. You can see its variance, and this turns out to be the bias squared. And the bias is 0, so you get bias squared plus the variance. That's how the quadratic. The risk under the quadratic loss turns out to be the so-called MSE, and the MSE has this composition. The proof is very simple. You can just repeat this x bar. I did it generally. So I haven't used the property of x bar here. If you do original delta, this happens. So this we can get bias squared with the variance. We'll get to this, but just a note, a hint of that. I haven't defined what bias is technically, but we'll get to that. Okay, any questions? Yes.
So, is the risk equaling for bias squared plus variance? Is that a general property?
No. That's a property of the quadratic loss, right? The risk under the quadratic loss.
So anytime the square loss is used, that applies?
That's true. Yes. You can say it's a property, the MSE, mean squared error. So this is called mean squared error. Mean squared error. Right? So this particular risk is called MSE. MSE has this bias against decomposition. But we'll see the general risk function would not necessarily have this. People would like to think that there is a bias variance decomposition inherent, but it's not as clean. And this is like a source of a lot of issues. People still talk about bias variance decomposition for general risk functions.
Is that, square loss is most commonly used?
Depends on the problem, right? So for problems like this, where the parameter is continuous, oftentimes it's the most common. For, let's say, classification problem, like binary case, this is often not used. Like 0-1 loss is used, but 0-1 loss is not nice, then other losses are used. In robust regression, for example, you can replace it with L1, that would be different. There's the Huber loss, which like tapers off the large value. So you can just do a lot of things. This is the easiest, like the most classical, and because you can square things, that's the main thing. Things simplify. So people start with this, but it's up to you. Right? Any other questions? Okay, so now I'm gonna plot these the way that we did for the simpler example. And this is what we get. Okay, you already know the punchline here. Unfortunately, I gave it away. But the thing is, you can see there is, so this is for n equal 10. This is for n equal to 50, like zoomed in. You can see like the different ones are colored differently. So delta 1 is the sample mean. The green one is the one that just oh sorry, not this delta one is not the sample mean. Which one is the sample mean? The sample mean is 0 at the both ends, right? So right, these two are similar, but this is the scaled down version of that. So 0 at both ends. So the green one is this constant estimator. Oh, sorry, yeah. So so this is the delta 4, just throws everything out except the first one. This guy is really the sample mean, yeah, so sample mean. And you can see this is the same shape as delta 4, but scaled out. Like this kind of n base. Delta 2 is the constant one, and delta 2 is the string. So you can see again, we have conflicting information. Okay, so we can't necessarily compare directly all estimators, but I can rule out one from this picture. So there's one that I can safely discard. Delta 4, why? Great, so delta 1 uniformly outperforms delta 4. Uniform with all lines of theta, so there is no need to keep. So you'd say that this one is a dominated or renders it inadmissible. So the term is inadmissible. So delta 4 is inadmissible because there is a competing estimator who means it, or it's as good as it is. So at these points, it's as good as it is, and all the other points, at least one point it keeps the straight combination, so this is inadmissible. We can throw out delta 4. But for the other ones, we can't really decide. Okay, that's the issue. So as the sample size grows, you can see it's not going to go away. This constant estimator seems to be very bad, but it turns out to be really good with the actual data one has. If you have a third point, this is a very good estimate. But you can't be sure. So somehow delta 2 is not necessary. You imagine delta 2 is not a good estimator, but at this point, you can't rule it out. Okay. And these two estimators are really hard to compare, right? So they're very close. This one is like going to be like almost flat. And this one goes very good at if you're deterministic, but worse if you're near 1/2. Okay. And so at this point, we have to decide what we want to do. There are a couple of things to do to deal with this issue, and then we try to explore those. Okay. So one idea is to try to reduce the entire risk function to a number. So somehow summarize it to a number, and then numbers can be compared. So that's the first approach. At least that's one way of viewing the fixing the issue. So we can take the average with respect to some weight on the theta space. So weighting of the theta. So let's say if I know that my theta is going to be like close to this rather than this, I put a weight function like that on theta, then I can take a weighted average of the values of the risk like this. So pi would be my weighting function. And this pi would be really the prior in the Bayesian approach. So Bayesian approach can be viewed in this fashion through the lens of decision theory as putting a weight on the space of theta to be able to like measure an average risk. So this gives you a weighted average risk. You can think of it as Bayesian approach. Bayesian approach is not necessarily viewed this way, but if you are a decision theorist, you view Bayesian approaches as doing this. Frequentists usually like don't treat theta. So in this fashion, we'll see. This is equivalent to assuming theta being random with this prior distribution. Frequentists don't like assuming theta to be random. So what we usually do, they take the maximum risk. That's the criteria that's very favored among frequentists. So they look at the maximum risk, and the maximum risk of this sample mean is worse than this. So this just means that the strange estimator in the minimax criteria is called minimax. So the estimator that minimizes the maximum risk. In the minimax sense, the blue is better. And then you try to find the one that minimizes this minimax risk. The other one is to restrict the class of estimators. Maybe if we restrict our class, then we can compare them uniformly everywhere. This leads to the idea of unbiasedness, uniformly variance unbiased, equivariance, etc. This one we'll see. And the other one is just rule out all the ones that are dominated and keep the rest. So this we already talked a little bit. I'm going to talk a little bit more about later. But we'll mostly focus on this first, and then talk a little bit about this. So this leads to some interesting theory. Yeah.
Like all those years, unbound.
The what?
What if they are all unbound?
The risk.
Yeah, I guess you compare it to that maximum. What if you're present with this?
You're going to assume that okay, so you're thinking of the case when the risk is unbound. So you're saying like for every estimate, then it means like for every estimate that the maximum is unbound, then like we throw our hands up. Because the issue is like there could be some estimators for which the maximum unbounded. Hopefully there is one estimator for which the maximum is unbounded. Right? But if it's unbounded, then you have other issues to worry about. In our case, it doesn't happen. So let's say the space is compact and this is completely. Right, that's a good question. Any other questions? Okay, I'll see you guys next time. Thank you.